Hey folks, so today we're going to talk about telescopes. Now, it's astronomy. When most people think about astronomy, they think about telescopes, and understandably so, because a lot of the things that we're going to be looking at are either so far away or just so naturally dim that you can't see them with your naked eye. And so, what we need is something that can increase the brightness of these objects. And that's going to be one of the key things I'm going to be talking about today. The sole and only purpose of a telescope is to gather light. Does not make things bigger. It doesn't make them closer or anything like that. It's just gathering light so that they're brighter, so that you can see those fainter objects. And so today you're going to figure out exactly how those telescopes work. All right, let's get started. So have your class notes out. This is tool 4. The class notes, remember, are the front and back of one page. Looks something like this. Go ahead and pause the video till you have that out. There's got a number of things you're going to be writing on the class notes this time. Ready to go? All right, let's get underway. So you have two perfectly good telescopes inside your head. Remember that the way the eye works is the light, we've got these light rays coming in, and then you have a lens here that focuses those light rays down onto your retina. And it does that by bending light. So here's a term that you need. Refraction is bending light. So anytime I have something that's refracting, it's bending light. You've probably seen this if you've ever put a straw in a glass of water. You put the straw in the glass of water and it looks like it's bent like that. It looks like the straw is broken. So what's happening is when the light from the straw that's in the glass hits the glass, it bends. Your eye isn't smart enough to follow that bend, so it just thinks that the light came from back here, and so that's why it looks like the straw is broken. It looks like it's offset that way. So that's all that is. That's refracting. So the lens is refracting, it's bending the light so that they all come together at this point right here, which should lie right on your retina. Now, this retina, the key here is that your retina needs a certain amount of energy to be able to be stimulated. If it doesn't receive that threshold of energy, nothing happens. If it receives more energy than its threshold, it'll send a signal down the optic nerve here that goes up to your brain. And that's how you actually see. It's not your eyes that are seeing, it's your brain that's seeing. In fact, it's possible there are certain kinds of brain damage, like if you get hit right about here, you can damage the brain in such a way that you can go blind even though your eyes are perfectly healthy. So what's the whole key thing here is that we got to be able to get enough energy to stimulate that optic nerve right here, for the retina to stimulate the optic nerve. If not, you're not going to see it. So let's take a look at this lens in a little more detail here. Now, go over to your class notes. You'll see this here. What I want you to do is pause the video, and I want you to extend out these light rays. And you see how each light ray is being bent by the glass. Some's being bent more than others. When it comes straight in the middle, it's going to go straight through. So pause the video, connect those out, and see what you see. Did you pause the video? Okay. So let's see if I can find my pen here. So you should have something that looks something like this. And you should see that all of those light rays pass right here in the center in a space that we call the focus. And when you focus your camera, what you're doing is you're adjusting the properties of the lens so that that focal point, that point right there where the light comes together, falls directly on the film or on the CCD chip or whatever if you have a digital camera. So that point is the focus. This distance from the center of the lens to the focus is called the focal length. And this is the primary measurement that we use for eyepieces. When we talk about, a 40 millimeter lens, we're not talking about how wide it is. We're not talking about its diameter. We're talking about how far back it focuses from the lens itself, because that's really what matters, is what that focal length is. So that's going to be real important to keep in mind. We're talking about the focal length, not necessarily the diameter of the lens here. So the key thing here is that the only purpose of a telescope is to gather light. That's it, nothing more. So each one of these individual light rays has a certain amount of energy. But when I take all of those light rays together and concentrate them, now all that energy is focused right there. How many of you ever fried ants with a magnifying glass? Come on, admit it. It's a lot of fun. If you haven't tried it, you should do it. Well, X-Files notwithstanding, if you walk out into the sunlight, you're not just going to burst into flames. unless you're a vampire, right? Because real vampires don't sparkle. So the what's happening here then, if you're like, well, if I don't burst into flames, how am I getting fried ants? Well, each individual light ray from the sun doesn't have enough energy to start a fire. However, if I take a whole bunch of those and concentrate them right here, now I've got a lot of energy. And so now, fried ant. So a telescope is doing the same thing. We've got all of this distant objects out in space, and they're not putting out a whole lot of light because they're so far away. We're not receiving a whole lot of light. And so they look very faint to us. So what we need for that telescope is to gather a whole bunch of those light rays and concentrate them, because if there's not enough energy to stimulate your optic nerve, you're not going to see it. So the telescope is not making things closer, it's not making things bigger, it's doing nothing but gather light. That's it, nothing else. All right, and that's real important. So when you go outside at night, all of the light from every star in the universe is shining on your eye. It's just that it's not enough energy for it to trigger your optic nerve, so you don't see it. When you look through a telescope, you put your eye to that eyepiece of the telescope. Now that telescope has gathered in a whole lot of those light rays. Now there's enough energy to stimulate your optic nerve, and presto, you can see it. So it really is as simple as that. So the purpose of a telescope is to gather light. That's it, nothing else. Keep that in your mind. Now, for what determines the properties of this focal length lens, the focal length that you have here, depends upon the curvature of the lens, how curved it is, and how thick it is. And if you think about it, that makes sense. The more glass that it has to move through, the more it's going to get bent. The more that glass is curved, the more it's going to get bent. I mean, you don't burst into flames when you stand in front of your window, right? That's because your window is very flat. And so there's not much curvature to it. So any focal point would be so far out, it would be, in another room or something, or probably outside of your house. So the more curved it is, the shorter the focal length is going to be. And the thicker the lens is, the shorter the focal length is going to be. Let's go back to the eye here. So let's suppose that for a lot of people, myself included, if when this light comes in, the lens actually bends it too much. So everything focuses right here instead of on the retina the way it's supposed to. And so on the retina, you get this fuzzy image. This is nearsightedness. It's actually called myopia. So what's happening is your lens is too thick and too curved, and so everything is focusing where ahead of the retina. So one way to fix this is to kind of pre-bend the light. So you take a lens that looks like this, and I'm going to try to draw it with the pen, which is a little difficult, but it looks kind of like that. It's a negative lens. So what it's doing is it's spreading the light out a little bit so that when it hits the lens, it focuses back on the retina. So that's what glasses and contacts are doing for you, is that it's spreading the light out so when it hits your lens, it bends back onto the retina. Now there's some other things that you can do for that. When I was in graduate school, I had a procedure called a radial keratotomy, RK. And what they do with that is they actually cut 12 slits into your eyeball with a knife. So the surgeon comes in and they're holding your eye open like this. You're awake the whole time. They don't put you out. They give you a Valium to kind of make you chill a little bit because, it's a little nerve-wracking to see that knife coming straight for your eyeball. But so he's holding your eye open like this, and then he pushes down on the lens to make each one of those cuts from there. Now, there's not a lot of nerves in the lens of your eye. Whenever your eye hurts, it's usually the muscle that's hurting, not the lens itself. So he makes those cuts, and you really can't tell that he's making a cut. The only time you can tell he's making a cut is you see the surgical light up above you. And whenever he pushes down on your eyeball, it goes like that. And so it just kind of wrinkles and then comes back. And what he is doing is when he puts those slits in your eye, it makes the curvature of your lens relax a little bit because of the slits. And so when it relaxes, that decreases the curvature, so the focal point moves outward until it falls right back on your retina. And the magic of it is he finishes this, you sit up and you can see. And it's just like that. So I didn't need glasses for a long time. I just got these a few years ago. But the idea was to change the curvature of the lens. Now, my wife, who was also nearsighted, was like, not just no, but heck no, am I going to let you cut on my eyeball with a knife, right? Because think about it, you're trusting to the skill of that surgeon. And and if he's coming in like this, that's probably not what you want. And the last thing you want to hear is oops, right? So that procedure never really caught on very much, even though I had it done, was pretty happy with it. So several years later, they had something called LASIK, and some of you have had it, some of you have heard of it, that sort of thing. But what they're doing with LASIK is they do cut to lift this part of the lens of the eye up, but then they shine a laser on it, and they're vaporizing part of the eye. So you're making the lens less thick. They're making it thinner. And remember, if I have a thinner lens, it's not going to bend the light as much. And so then that also pushes that focal point back out onto the retina. And so it works just as well. The difference is that you can control it a whole lot more easily. In fact, the computer actually controls where the laser goes. So the surgeon takes a scan of your eye and then uses that to program the laser, and then pushes the button, goes and gets a cup of coffee while it's going on. So it's all kind of magic. And you'll actually see better after LASIK than you will with even glasses or contacts, because nobody has a perfectly smooth eye. It's an organic material, so you've got bumps and things like that in your eye. That laser can actually completely smooth your eye and give you a perfect curvature on there, so that you'll see better than you would with glasses or contacts. So key point here, the focal length, which is the primary property of the lens, is controlled by the thickness and the curvature. Change either one of those and you can move where that focal length is. It is not controlled by the diameter of the lens. The diameter of the lens has absolutely nothing to do with this. And if we were doing this in person in the lab, we actually give you a bunch of lenses, all of which have exactly the same diameter, but they all have different focal lengths, and we have you build a telescope. All right, so this focal length then is what we're going to be talking about when we're talking about the size of lenses. We're not talking about the diameter most of the time, and if we are, I'll tell you that specifically. But most of the time, we're talking about the focal length, where it focuses back from the lens. So you may say, well, Kilo, I've looked through a telescope and by God, things are bigger. Well, yes, but that's not the telescope that's doing that. The telescope is this primary lens. It's called the objective lens. So the primary lens here, that's the telescope. You can't change that. But we normally put right at the focus here, we put a secondary lens that's more commonly called the eyepiece. And it's the eyepiece that's making things look bigger. So here's a formula that you're going to need to learn. The magnification is equal to the focal length of the objective. Remember, the focal length is how far out it focuses from the surface of the lens, or from the center of the lens, divided by the focal length of the eyepiece. So before we do any math, though, because we only need to do math if we need details. In this case, let's look at what's happening with the formula here. So let's suppose that I chose an eyepiece, a focal length eyepiece with a smaller focal length. What is going to happen to the overall magnification that I'm going to see? Is it going to increase or is it going to decrease? Pause the video and think about that. Okay, hopefully you did pause the video, because this technique is what we're going to be using all semester long. So if the focal length goes down, you see that it's in the bottom of that fraction there? So if that bottom number gets smaller, the overall fraction gets bigger. So they're inversely proportional. So if the focal length of the eyepiece gets smaller, the magnification gets bigger. Let's remind ourselves and see why that works. So if I have 1/4, all right, now I'm going to make that bottom number, I'm going to make it smaller. Do you see that the overall fraction got bigger? So they're inversely proportional. Now, two things that are in the top, if the focal length of the objective goes up, well, now that top number is getting bigger. So instead of 1/4, I might have 2/4, which is also, of course, 1/2. But then, so that means that the overall magnification goes up. So if it's in the top, if it's in the top like it is here, then they're directly proportional. They change in the same direction. If I've got one in the top and one in the bottom, then they're inversely proportional. They're going to go in opposite directions. And so what you're going to have to do in some of the exercises here is you're going to have to think about that inversely and directly proportional. You're not going to do the math. I'm not giving you the numbers for it. But you can still come up with some decisions based on just inversely and directly proportional. Okay, so this is why things look bigger or smaller when you look through the telescope. So if I have, for example, my camera has dimmed here, but hopefully it'll come back. There it is. So let's suppose I have a 40 millimeter objective. Now remember, that's not the diameter of the lens. That's how far from the center of the lens it focuses. And let's suppose I have a 20 millimeter eyepiece. What's the magnification? Suppose I need to know the exact magnification. Now I'll do the math. Well, 40 divided by 20 is 2. And we usually write that as 2 power. Everything looks twice as big. Now, how many of you have ever looked through a pair of binoculars backwards? Oh, come on, admit it. We've all done it, right? Okay, so what do things look like when you look through a pair of binoculars backwards? Well, they look really small, right? So why is that? This formula is telling you why. Because any lens can be an objective, any lens can be an eyepiece. There's nothing special about the lens itself that makes it an objective or an eyepiece. It's how it's used. So if that lens is next to your eye, it's the eyepiece. If that lens is the one the light hits first, well, then that's the primary lens or the objective. So let's suppose that this 40 millimeter and 20 millimeter lens system is our set of binoculars we're looking at normally. Now, if I turn them around backwards, now the 40 millimeter lens is next to my eye, so it is the eyepiece. Let's find my mouse again. Here we go. So that means that the objective is the 20 millimeter eyepiece, and the eyepiece is the 20 millimeter lens, and the eyepiece is the 40 millimeter lens. And so what magnification do I get now? 1/2 power, so everything looks half size. So this formula is the reason why things look smaller when you look through a pair of binoculars backwards. All right. So look at the table that you have down at the bottom there. On the bottom of page 1. I want you to pause the video, use the formula, and I want you to think about this. I want you to figure out the characteristic for a larger focal length eyepiece or a smaller focal length. We're going to assume we've got the same telescope, so the objective's not going to change, because most astronomers have one telescope and then a whole kit full of eyepieces that they can swap out. So if I put in a larger focal length eyepiece, is the magnification going to increase, decrease, or stay the same? Pause the video, think about it. What'd you get? So if I have a larger focal length eyepiece, then think about the formula. Let's write it out here. Magnification is the focal length of the objective, which is the telescope, divided by the focal length of the eyepiece. So if I have a larger focal length eyepiece, they are inversely proportional. So the magnification is going to go down. It's going to decrease. Good. All right, so now what if I put a smaller eyepiece? Now you could probably figure this out by process of elimination, but pretend you don't know. Go through the steps. So pause the video, figure out what is going to happen to the magnification if I use a smaller focal length eyepiece. Did you really work it out? You should, because you need the practice for this. So in this case then, let's go ahead and get rid of these. In this case, I've got a smaller focal length eyepiece, so that goes down. They're inversely proportional. So as one goes down, the other goes up. So that means the magnification is going to increase. Okay. So a typical eyepiece might be a 40 millimeter eyepiece, might be a 25 millimeter eyepiece. That might be a larger focal length eyepiece. So they're going to have a low magnification. On the other hand, a 9 millimeter eyepiece is going to have a very small focal length, and so it's going to have a much higher magnification. And so you can control how much magnification you get by swapping those around. Now, the diameter of the lens doesn't affect the magnification at all, not even a little bit. However, what the diameter of the lens does determine is how much light you're gathering. So what I want you to do, you've got a chart here. I want you to pause the video, and I want you to compare lens A and lens B. And I want you to fill out this chart that's here at the top of page 2 of your class notes. Pause the video, do that now. Okay, so did you pause the video? Do make sure that you're thinking about every one of these. The thought process that goes on is what I'm trying to teach you here. I don't want you to memorize stuff. I want you to think about the thought process, and that's why I'm giving you the practice with that thought process. All right, so which one has the larger diameter lens? Lens A or lens B? Well, obviously that's going to be lens A. So when we're talking about diameter, we're not talking about where it focuses now. That's the focal length. The diameter of the lens is how wide the circle of the lens is from there. So lens A is going to have the larger diameter lens. All right, well, which one is gathering more light rays? We'll take a look. So the way we've idealized this here, the light rays are the same distance apart. And in reality, this thing is being covered with light rays. But do you see that lens A is going to receive more light rays than lens B just because it's bigger. It's a bigger bucket. Think about taking a bucket out and catching rain. I know in Arizona, not much rain, but think about monsoons. The bigger the bucket, the more water you're going to trap. So here I'm getting, say, 5 light rays. Here I'm only getting 3. So lens A is going to gather more light rays. So which then is gathering more energy? Well, each one of these light rays, each individual light ray has the same energy because they're coming from the same object. So if each light ray has the same energy then, and I'm getting more of them with lens A, then that means lens A must be receiving more energy. So now this last one, you've got to think about how your eye works. Remember that your optic nerve is sensing energy, not light, it's sensing energy. And so the more energy that optic nerve receives from the retina, then your brain perceives it as being brighter. So lens A, the image is going to seem brighter through lens A. You see how that works? Because it's gathering more light. So the sole and only purpose of the telescope is to gather light. That's it, nothing else. Okay, so you may wonder, well, Kilo, why don't we just have the highest magnification we can possibly get all the time? Well, that's because just like in economics, there's no such thing as a free lunch. You're always going to give up something if you get something. So in this case, if you have a higher magnification, you're going to see that you have a lower field of view. Let's look at the 2 images that we have here. These were taken with the same telescope, so same objective focal length, but we've got 2 different focal length eyepieces in there. So look at the chart that you have on page 2 here. Which one of these 2 images, eyepiece A or eyepiece B, has a higher magnification, or do they have the same magnification? Take a look. We're going to do this one together. So pause the video, think about it. Okay, well, obviously eyepiece B has the higher magnification. Do you see how that works? Well, and some people say, oh, well, yeah, it's higher magnification because it's closer. Well, it's not really closer. Think about it. We haven't brought the cars closer to us. We've made them bigger. And so in here, we've made the image of the car in eyepiece B is quite a bit bigger. So it's got the higher magnification. So when we look at the analysis here then, eyepiece B has the higher magnification. All right, so which one then has the larger field of view? So field of view means how much of the image you can see in your telescope from that. So eyepiece A has the larger field of view because I can see more of this car. In a telescope, would be I could see more of the sky from that. So eyepiece A has a larger field of view. Does that make sense to everybody? You see why? Okay. So when we fill out our chart, then eyepiece A has the larger field of view. Now, here's the part where I want you to think through it. We're not going to do math because you don't have any numbers. You can't do any math. But you can still use that equation to figure out which of these images was taken with the longer focal length eyepiece, either eyepiece A or eyepiece B. So let's write down our formula here. So the magnification is equal to the focal length of the objective, which is the telescope, so that's not going to change, divided by the focal length of the eyepiece. Now, if we've got a longer focal length eyepiece, if that's gotten bigger, what's going to happen to the magnification? Well, they're inversely proportional, so the magnification goes down. Remember, I've got one in the top and one in the bottom. If they were both in the top, then they would be directly proportional. They'll change in the same way. But since I've got one in the top and one in the bottom, they change in the opposite direction. So as the focal length of the eyepiece in the bottom goes up, the total magnification is going to go down. You don't need to do any math. You don't need to put any numbers in, but you can still see that. All right, so the longer focal length eyepiece then causes a greater magnification. Now you tell me, think about it. Which has the higher magnification, eyepiece A or eyepiece B? If you look right here, that's going to be, you've already figured it out from that. So if I have a lower magnification, right? Eyepiece A has a lower magnification. Think about that. Eyepiece A has a lower magnification. It also has a larger field of view. So if the focal length of the eyepiece goes up, then the total magnification goes down, and so I have a larger field of view, and that's going to be eyepiece A. So just by looking at the images here, you were able to figure out that eyepiece A must have the larger focal length. And like I said, a typical focal length for an eyepiece for a large focal length eyepiece might be 40 millimeters or maybe 25 millimeters. For a small focal length eyepiece, it might be 9 millimeters, somewhere right now. All right. So up to this point, we've been talking about refracting telescopes. A refracting telescope uses refraction. It uses bending of light through glass. So the key thing about a refracting telescope is it's using glass lenses. But that's not the only way that you can get things to focus. We can also use a mirror. So in this case, if I've got a curved mirror, look at the reflecting telescope diagram here. And these are down at the bottom of the page in your class notes. So when the light comes in, the light rays come in, they hit this curved surface and they get reflected down like this. This red ray comes in, gets reflected, and comes like this. And you should be able to see that all of the light rays are going to get concentrated right here. So I've got to focus exactly like I do with the refracting telescope. And so my focal length would be the distance from the mirror to the focal point right here. Now there is one small problem with this. With a reflecting telescope, I would normally want to put my eye right here, right? Well, if I put my eye right there, then all I'm going to see is my face, which is probably not why you bought the telescope. You probably wanted to see the stars. So what we have to do is we have to put a pick-off mirror right here that sends that image up through the side of the telescope. And then I put my eyepiece here mounted actually on the side of the telescope. And it may be towards the back. It's often on the end of the telescope, far over there. So this is called a Newtonian focus reflecting telescope. All three of these are reflecting telescopes. This is a particular flavor called a Newtonian focus. The reason why I bring that up is we actually at GCC have telescopes that you can check out. As soon as you finish this lecture, you're qualified to check those out. You can find any of the astronomy instructors, and we'd be happy to check one out. You got to go to GCC Maine to do that. But you can check it out for a weekend or whatever. And the ones that we check out to you are Newtonian focus. That means that the eyepiece is going to be on the side. And that's great. It's easy to do. However, they do have a small disadvantage. When we're doing research astronomy, a lot of times we have other detectors that we're going to be talking about next time. But it might be a camera, it might be a light sensor or things like that. So when I've got a camera on a Newtonian focus, I've got this big honker piece of equipment hanging on the end of the telescope. And so the telescope is not going to be terribly stable. And I need it to be focused and stable right on that object that I'm looking at. So for research telescopes, a better idea, we can drill a tiny, tiny hole in the back of the mirror here. And then turn my pick-off mirror so that when the light gets focused on it, it comes back and shines through the back of the mirror. And then I can put my eyepiece actually on the bottom of the telescope. So if this is the telescope, it goes on the back right there. And that could also be a camera or a spectrometer or whatever I want to put on there. So that's called a Cassegrain focus telescope. This is the type of telescope that we have up at GCC North in our observatory. So if you ever come to one of our astronomy nights, then you'll get a chance to actually look through a Cassegrain focus telescope. Still a reflecting telescope. It's just matters where we put the focus. If it's on the end, it's a Newtonian focus. If it's in the back, it's a Cassegrain focus. That's it. So one thing you should know, though, are the advantages and the disadvantages of the different telescopes. So a refracting telescope really only has one advantage. The focal length tends to be very long compared to the diameter of the telescope. And it's not to say that I can't make a reflecting telescope with a long focal length. I can. But you see how small that lens is. That's maybe, a 3-inch lens. But the focal length, might be as much as 2 or 3 feet from that. So think about it. If I have a long focal length objective, what does that tend to do to the magnification? Let's write our formula down. So if this is the magnification, the focal length of the objective, that's the telescope, divided by the focal length of the eyepiece. Now in this case, I'm going to keep the same eyepiece, but I'm actually going to have a long focal length objective. What happens to the magnification? So now they're both in the top. Do you see that? So they're directly proportional. So that means if I have a long focal length objective telescope for the same eyepiece, I'm going to get a much larger magnification. So refracting telescopes tend to have very long focal lengths, and so they have very high magnifications. Now, the disadvantage to this is that they're going to tend to have very small diameters. And so, like I said, this one's only about maybe 3 inches or so. It means it doesn't gather much light. So if you're looking at something bright, that's fine. You don't need it. The moon, the planets, Mercury, Venus, Earth, Mars, Saturn, all of this stuff. And I say Earth intentionally because when you look through binoculars, they're generally refracting telescopes because most of the time you're using binoculars during the day. You don't need a whole lot of extra light. You've got plenty of light. The sun's shining, right? Same thing with a pirate's spyglass. If he's scanning for objects on the horizon, what he wants is to make things bigger. He doesn't care about gathering light. He wants to make things bigger. And so a refracting telescope is perfect for that. So with a refracting telescope, you're more easily able to see details on the surface of Mars, for example. So that's the big advantage. Mars is bright. You don't need a big telescope to see Mars. You can see Mars with your naked eye. So a refracting telescope is a good choice. The other problem is they're pretty expensive. You have to grind those lenses, to grind that glass. You have to grind it very, very precisely, much more precisely than you do with your glasses, for example. So that's going to make it pretty expensive. Obviously, it's fragile. It's glass. If you drop it, it's going to shatter. So, and there goes your, $400 or $500 telescope from that. This last one is one you may not have heard of. This is called chromatic aberration. Literally means color error. And if you've ever seen a prism, a triangular prism, when the light shines through, it bends, but the blue and the red light are bent differently. And so that spreads it out a little bit more and makes a rainbow. So a prism makes a rainbow that way. All glass does that to a certain extent. So when you look through a refracting telescope, sometimes you might see kind of a rainbow colored halo around the object from that. There's nothing you can do about that. That's just because it's traveling through the lens. And so it's going to get refracted a little bit differently. Now, the advantages and disadvantages of a reflecting telescope are basically the opposite. This, by the way, this is the actual telescope that you can check out from us. And it's about, maybe 3 feet tall, something like that. And you can see that the mirror is back here. So it is a reflecting telescope. The eyepiece is on the side. So is that a Newtonian focused telescope or a Cassegrain focused telescope? That one's a Newtonian. So there's a pick-off mirror right here. So the light comes in, hits the mirror, hits the pick-off mirror, and then comes out through the eyepiece, and you look at it through the side. So it's got a shorter focal length compared to the diameter. Now you may say, well, yeah, Kilo, that's a really long focal length. And that's true, it is. But the diameter of that lens is much bigger. These are 6-inch telescopes, so it's over twice as big as the smaller little refracting telescopes you'll see. Because it's got a large diameter, that means it's going to gather more light. That means you can see very faint objects. You can see the moons of Jupiter. You can see the rings of Saturn. You can see galaxies and things like that with this. They're less expensive because mirrors are very easy to make. You just take your mount for it and you basically spray aluminum and polish it on that. And that's it. That's all that you need. So you can make these things as big as you want. They're fairly inexpensive to make. They're very sturdy because the mirror is just coated aluminum. It's not glass from that. So it doesn't break very easily. That's the reason why we're willing to check them out to you. And also because it doesn't actually pass through the lens, there's no chromatic aberration. So for that reason, most of the research telescopes that you're going to find that astronomers use are going to be reflecting telescopes. About the only time that you're ever going to want to use a refracting telescope is if you're strictly going to be looking at planetary objects like the moon or Mars or Venus or something like that. Even then, a reflecting telescope can do it. And so you can also use that reflecting telescope for a lot of other things. So let's look at some of the different telescopes that are out there. This is the Yerkes 40-inch telescope. This is in the United Kingdom. It's just outside of London. This is the largest refracting telescope in the world. It's 40 inches in diameter. The lens is 40 inches in diameter. And if there were a human standing here, they'd be about the same height from the floor to the bottom of the telescope here. So this is a really, really huge telescope. Notice how long the focal length is. So for a long focal length objective, am I getting a high magnification or low magnification? They're both in the top, right? So it's the objective here. So that means if they're both in the top, that means they're directly proportional. So this telescope has an extremely high magnification. So it's really good for looking at the surface of Mars or the moon, for example. But this is about as big as you can make it, because the problem that you're going to have with lenses is glass is actually a slow flowing liquid. It's not actually a solid. If you ever go back east and you look at some of these 300-year-old churches, their stained glass windows are actually wider, they're thicker down at the bottom than they are at the top, because over 3 centuries, that glass has been slowly flowing downward. Well, the bigger the lens, the more that distortion is going to happen. And so there's a maximum size at which you just can't keep the lens to keep it shape, because remember, it has to be very, very precise. So 40 inches is about as big as you're ever going to find, and even this one's kind of pushing it a little bit. Most all of the other large telescopes that you're going to see in astronomy are going to be reflecting telescopes. So let's look at those. So this is the Subaru 8mm telescope. Subaru, by the way, is the Japanese word for the Pleiades, the Seven Sisters. If you've ever seen Subaru the car, their symbol is the Pleiades. So it's a constellation. So that's where that comes from. But this is on top of Mauna Kea in Hawaii, which Mauna Kea is the highest mountain in the world. You're like, wait a minute, isn't Mount Everest the highest in the world? Well, Mount Everest is the highest above sea level. Mauna Kea is the highest from bottom to top, but most of the mountain is actually below the water in the ocean. So it's still very high. It's still the highest point in Hawaii. So we put the telescope up there because we can get up out of the atmosphere. We'll talk about that a little later. So to give you an idea of how big this thing is, you see these three little frames right here? That's about the width of a Subaru car from that. So this thing is really huge. The light comes in. This is the primary mirror down here. It's 8 meters across. And as I said, that's roughly 4 rooms in your house. It hits that light, hits the pick-off mirror here, and then gets reflected back through a hole in the central mirror. And that's where we observe from. This is just a walkway for maintenance, things like that. And you may say, well, Kilo, why isn't there a tube around that telescope? Every telescope I've ever seen has had a tube. Well, the only thing that tube is doing for you is it's keeping the air from flowing in between the primary lens and the pick-off mirror there. Well, in this case, what we do is we build a big dome over the telescope to keep that air out, and then you can just barely see the doors of the dome up here. Those open up and then turn with the telescope. Well, since the dome is keeping the air from traveling in between, you don't need a tube. It's just wasted money and wasted mass that you're going to have to move around. So most very large telescopes don't actually have a tube around them because you don't need it. This is the largest single mirror telescope in the world. This is owned by Spain and the Canary Islands. This is a fisheye view, so it's a little distorted to how to tell, but you can see the people down here and get an idea of how big this is. So this is 10.4 meters. All right, so quick review. Every telescope is made up of 2 things. It's made of a primary, also called the objective lens. That's the telescope itself. You can't change that. If you're changing that, you've got a different telescope at that point. So the sole purpose of that telescope is to gather light. That's your light bucket there. Then I put an eyepiece on so that I can control the magnification in the field of view. Now, you may say, well, why wouldn't I want that high magnification then? Well, if I lose the field of view, then I'm not able to scan the sky. So for example, have you ever seen these name a star things? You know what I'm talking about? Where you can send your money off and they'll name a star for your sweetie or whatever. All of those are fake. They are completely fake. There is the only people who are authorized to name astronomical objects is the International Astronomical Union, and they do not allow anybody to name stars. So yeah, if you send your money to this company, they'll write that name down in their little book and they won't give it to anybody else. But this company will, and this company will, and this company will. So if you really want to name a star for your sweetie, get into Photoshop, make yourself a nice, pretty certificate, print it out, and give it to them because it means exactly the same thing. However, the IAU will let you name an object if you have discovered an asteroid or a comet. And there are hundreds of asteroids being discovered every single month by amateurs just like yourself because it's very easy to do. You set up your telescope, you take a picture of the sky. Then about 4 hours later, you take another picture of the sky. Then when you on your computer, you blink them, like the flip books you had where you'd flip through the book and the little stick guide would move or whatever. So this is the same thing. The background stars stay in the same place. But if there was an asteroid there, it'll sit there and flash as you blink between the 2 pictures saying, congratulations, you're famous. Congratulations, you're famous. And so once you've discovered that, then you can submit it and you can name it for your sweetie from that. So there are people that this is their hobby. They just set up a telescope and they go out and discover asteroids. So if you want to do that, think about it. Do you want a large field of view or do you want a small field of view? Well, you want a large field of view so you can scan as much of the sky as possible. On the other hand, because magnification doesn't help you, you're never going to be able to magnify that asteroid enough to be able to see it, to see the surface of it. The only thing you're seeing is the light that's reflected from the sun, from that asteroid. So you want to scan as much of the field of view, as much of the sky as possible, which means you need a very low magnification. On the other hand, if you want to look at the surface of Mars or the surface of the moon, then you're going to want a high magnification. So you're going to want a short focal length eyepiece because you don't need a lot of field of view. So you'll swap out eyepieces all day long, but you generally only have one telescope. Know the two types of telescopes. A refractor uses lenses, a reflector uses mirrors. And you can remember that because you see your reflection in the mirror. Know the advantages and disadvantages of each type. You can scroll back through the video and review that if you need to. All right, so make sure that you've got your practice worksheet, download that, fill it out, and then as always, take a picture, scan it, and it'll be graded for accuracy. I'll post those grades on Monday. Okay, so the key things I want you to think about are the different kinds of telescopes and why we tend to use reflecting telescopes in professional astronomy as opposed to refracting. It's not to say refracting telescopes are useless. If you think about it, if you're looking for a high magnification, then you probably do actually want to use a refractor. And that's why your binoculars are using lenses, because that's giving you that refraction. Most of the time you're using binoculars during the day, you don't need to gather any light. It's bright, it's daytime. What you're looking is to make things bigger. And so a refracting telescope is easier to do that with. A pirate's spyglass, when he's scanning for ships on the horizon, that's typically going to be a refracting telescope. But if you're looking at distant objects, you need to gather that light. And that means you need as big a telescope as you can possibly get. And so in order to get a big telescope, unfortunately, you're going to have a reflecting telescope for that. It's got a lot of advantages and really not that many disadvantages. So if you get a chance, check out one of our telescopes. You can do that at the GCC main campus, and basically just need to find any one of the astronomy instructors, and you can sign away your firstborn child, and we'll let you check that out for a weekend or however long that you need to look for it. All right. Hope you take advantage of that. We'll see you next time.